Now, I know a lot of the people in the chat today are from various different backgrounds. Some of you might be new to machine learning, some might be new to JavaScript, or maybe new to both. So I want to make sure everyone's on the same starting point. And you might have had a few buzzwords in the industry, such as artificial intelligence, machine learning, or even deep learning. So let's go ahead and formalize what those actually are to make sure we all understand. Now, artificial intelligence, or AI for short, is essentially the science of making things smart, or more formally, human intelligence exhibited by machines. But this is actually a very broad term, and right now we're in a place where we do narrow AI. And essentially all that means is that we can do one or a few things as well or better than our human counterparts. So for example, object recognition. And a great example of object recognition is in the medical industry, where doctors are using AI systems to help them identify brain tumors in the grainy medical images that come back from the scans. And in the past, you had to rely on the human eyes to look for these subtle details in these images that are the telltale signs of a brain tumor. But now the AI can recognize these in milliseconds, which means faster diagnoses for you, and of course, more accurate results for the doctor as well. And this is just one example of how AI is affecting some of the industries out there, including healthcare. Now, machine learning, on the other hand, or ML for short, is an approach to achieve artificial intelligence that we just spoke about on the previous slide. And essentially, this is at the implementation level. This is the actual program that can learn to find patterns in the data presented to it. And the key thing about these systems is that they can be reused. So if I create a machine learning system that can recognize cats, I can use the same set of code without writing any new code to then recognize dogs, just by changing the input training data that I present to the program. And that's very, very powerful. Now, in the old days, when we did programming, if we're trying to make a spam filter for email classification, we may have had to have a bunch of conditional if statements, as you can see in the top right hand here. So if the email contains a certain word, then mark it as spam. If it contains a different word, mark it as spam. And that's good, but of course, this means the human has to maintain this list, and the spammer can just change the word slightly, and they then have to implement that. Otherwise, they can get past the system. Now, fast forward to today, and we now use machine learning to classify spam emails. And this is what Google uses behind the scenes as well. And essentially, we now have people like yourselves marking emails as spam. And then we can use mathematics and statistics to figure out what words are most likely to contribute to spam when they're in the context of other words around them, and all these other kind of patterns we can learn from the emails that are submitted. And now every night we can just run this training and essentially have this done for us. And we don't have to maintain these kind of lists ourselves. The machine learning will figure out all by itself what words are most likely to classify as spam. And there's many other different machine learning use cases out there. We've got computer vision for object detection, as you spoke about earlier. We've got numerical regressions, which simply means for some numerical input, can we predict some numerical output? So a good example of that is if the square footage of a house in San Francisco is 1,000 square feet, what do we predict the price of the house to be? It could be $1 million. And with enough training data, you can get a system to predict what that might be. Now, we've also got natural language, which is the understanding of human language itself, the sentences that we write down, things like toxicity detection or sentiment analysis to understand if a sentence is positive, negative, or neutral, that kind of stuff. We've got audio recognition, and any of you with a smartphone is probably already used to this with the smart digital assistants we have these days, things like the Google Assistant, which works surprisingly well, even in noisy environments. And that's because we've trained our machine learning in noisy environments to get the essence of the words, even with background noise. And then my personal favorite is generative examples, which are things like style transfer and creative applications of machine learning. And one of those examples is on the slide here today. This is actually research from NVIDIA, which is now about a year or two old, I think. And the key thing to note here is that these faces that you see on my slides are not real. None of these humans exist in real life. They're completely dreamt up. Just like if I asked you to imagine a purple cat right now, you could probably do so, even though you've never seen a purple cat before. And essentially, the machine learning system here has learned the essence of what a human face is, and then is able to mathematically generate new ones at will. And that's very, very powerful stuff. Now, deep learning, on the other hand, or DL for short, is a technique for implementing machine learning, which is the application we spoke about on the previous slide. And you can think of this as one of the algorithms you can choose in the application to make the machine learning come to life. And there's many other things out there you could use, and deep learning is one of those things. So just one algorithm. And a popular technique here is known as deep neural networks within this deep learning domain. And essentially, these are code structures that are arranged in layers that very loosely mimic how we believe the human brain to work, essentially learning patterns of patterns as you go deeper into the network. So if you bring this all together, you've got these three terms that you can see that are very interlinked. And they actually go back quite some time. These are not new ideas. They actually go back to the 1950s or so. And this is very interesting because you can see here the deep learning is the algorithm that drives the machine learning implementation, which is the program. And that gives us this illusion of artificial intelligence that we're trying to aim for, if you will. Now, the next logical question is, like, how do we train these machine learning systems? And for this, we're going to all pretend to be farmers. And we've got some apples, we've got some oranges, and we're trying to classify the difference between the two. So when we see a new piece of fruit in the future, we can understand what it is, maybe to put it into the correct box automatically or something like this with a robotic arm. Now, the first thing you need to do is figure out what features and attributes you can measure digitally that we can represent in numerical form. So we've got things like weight and color. Both of these are easy to measure using digital weighing scales or a regular RGB webcam, and they can be represented numerically just by a bunch of numbers. Now, if you go back to your high school mathematics and you plot these on a graph, let's say you take 50 apples and 50 oranges, you might end up with a scatter plot that looks something like this. And you can see the green apples are in the green spectrum of the x-axis here, the red apples are in the red spectrum, and the oranges are in the orange spectrum, but are slightly higher up because they're more juicy, they have more water in them, they're slightly heavier on average, so they're slightly higher up in the chart there. Now, if we can draw a line that separates the oranges from the apples, as you can see here with a dotted line, we can then say with some level of confidence for any new piece of fruit that we then measure the weight and color of, if it is above the line, it's probably going to be an orange, and if it's below the line, it's probably going to be an apple. And of course, there might be some outliers there that are incorrect, but most of the time it would be right. And this is the essence of what's going on behind the scenes for machine learning. If we can get a computer to figure out the equation of this line automatically for us, then it has the ability to learn and to classify things. And basically, machine learning is all about the separation of the data in such a way that you can then classify things in the future with a good reliability. Now, of course, if that's all it was, would be done and the presentation would be over. And of course, things get a little bit more complicated. So let's see why that might be. Now, the first thing is, what if you chose bad features or attributes? You can see here that if I chose ripeness and number of seeds, you might get a scatter plot like this. And here, there's no good way to split this data up. You can't even use a curved line to split this data very easily. And you might be, well, Jason, why would you choose such bad features for apples and oranges? And of course, ripeness and number of seeds, it's clear that's not going to give you a good separation of data. And for these trivial use cases, it's obvious. But for what about those brain tumors we saw earlier in the presentation? How would you define the features and attributes of those? Things get much more complicated when the problems become more abstract, when you're dealing with pixels in an image versus actual features you can measure using your digital apparatus. And then what about higher dimensions? In the previous examples, we had just 2 features and attributes. What if we had to have 3 features in order to separate the data? And you can see here, we've got the same plot as before, ripeness and number of seeds, but now we've added a 3rd dimension in the z-axis for weight. And you can see now that the oranges, which are a lighter orange color behind this kind of rectangle in 3D space, or a plane, if you will, have now been separated from the apples in the weight dimension. And we needed 3 dimensions to do this. And that's why we need to use a 3D graph to now draw this out. And instead of using a line, we're using a plane or this rectangle in 3D space, essentially. And the key thing to note here is that machine learning typically doesn't even use 3 dimensions. It uses tens, hundreds, thousands, even millions of dimensions. And as humans, we can't visualize this because we are used to dealing with 3D only in our day-to-day lives. However, the mathematics can deal with this. And instead of using a plane, which as you see here, you can use something called a hyperplane, which simply means 1 dimension less than the number of dimensions that you have. And just to reemphasize that point, this rectangle is 2 dimensions in a 3D space, right? So it's 1 dimension less than the number of dimensions we're actually trying to use here. And the same thing happens in the high dimensions as well. You just have to do it in mathematics, as we can't visualize it on a screen. But the principle is exactly the same. So it should be easy, right? We've got dogs, we've got mops. What could possibly go wrong? These are very 2 different objects. And essentially, some dogs can look like mops, as you can see on the screen here. And even I, as a human, can struggle to identify which one of these is a dog versus a mop. And if you look closely, some of them are actually very different to what you expect. And the reason I bring this up is that one of your biggest challenges as a machine learning engineer is finding enough unbiased training data for all of the features in the object you're trying to recognize. So if you're trying to recognize cats, you might need 10,000 images of cats taken at different stages of their life cycles, kittens versus adults, different breeds, different fur types, different fur colors and patterns, all taken in different lighting conditions, indoors, outdoors, different rotations and angles. And all of these things are required for the machine learning to then have understand the essence of what cat pixels truly consist of. And of course, the other thing to point out here is that data is not always images. It could be tabular data, it could be text, it could be sound recordings or sound samples, and much, much more. I use images in my presentations because it's much easier to visualize, but of course, it could be anything. So why do we want to do machine learning in JavaScript is the next logical question. And essentially, JavaScript can then run the machine learning anywhere that it can run. And right now, that is a lot of places. We can run in the web browser, on the server side, on desktop native, on mobile native, and even Internet of Things. And if we dive into each one of these stacks in more detail, you can see many of the technologies you might already be using. So the web browsers on the left-hand side there, we've got Node.js for server side, React Native for mobile native applications, Electron for desktop native applications, and even the Raspberry Pi can run Node, therefore we can run on the Raspberry Pi as well for Internet of Things. And JavaScript is one of the only languages out there that can run all of these environments without any additional plugins. And for that reason alone, it's a very powerful language to use for your prototyping and for machine learning. And with TensorFlow.js, which is the team that I represent, you can retrain via transfer learning, or you can write your own machine learning models completely from scratch, just like you might be doing in Python already, but in JavaScript, and run it in all the environments we just saw. And with that, it allows you to make anything you dream up, from augmented reality to sound recognition, sentiment analysis, conversational AI assistants, and much, much more. Now, depending how you want to use TensorFlow.js, there's 3 main ways, depending on your experience. And essentially, the first way, the easiest way, is to use our pre-trained models. These are really easy to use JavaScript classes for many common use cases. And here's just a few of them on the slides right now. We've got things like object detection, body segmentation, which allows you to understand what pixels in an image belong to the human body, pose estimation to understand where the skeleton is. We've got things for your face and your hands to understand the precise positioning of your face and hands. We've got BERT, which is a natural language processing model to do very advanced understanding of human language, and many, many others. You can check out tensorflow.org/js/models to see more of those if you wish after the show. But I'm going to go through some of them right now just to give you a flavor of what they're actually capable of. And the first one is object recognition. This is known as COCO-SSD behind the scenes. That's just the name, very fancy name for the model architecture, but essentially it's called object recognition. And it's been trained already on 90 common objects, things like cats, dogs, TVs, humans, things you might see in everyday life. There's 90 common objects it already knows how to classify. And that means you can present an image like the one on the right-hand side here, and it will give you the bounding box information for the objects it can recognize in the image, like these 2 dogs. And that's great because then it allows you to localize in the image where the object is. And if you can do that, you can also then count how many of the object there are. So there's 2 dogs in this image, and we can see where they're sitting or standing. Now, this is different to image recognition, which only will tell you that there's a dog in the image, but not where or how many. And that's the difference between image recognition versus object recognition. So let's go ahead and see this in action. I've got a live demo for you all here. And hopefully now you can see my screen. And this is just a glitch.com example that I've made together using regular HTML, CSS, and JavaScript and some TensorFlow.js. And if I click on any of these images, you can see I can get real-time classifications as I click of the objects contained within. So you can imagine here, we can see the dog and the bowl of treats, and we could very easily create a very smart webcam that would recognize when my dog is on the sofa or something like this. And you could then send yourself an alert to notify you of this situation. And you could do this in a matter of minutes. It's not hard to make this kind of code. And just to show how far this can go, we can enable the webcam as well here. And you can see I'm now live talking to you right now. And you can see me in this running at high frames per second, the real-time classification of my webcam stream. And you can see it's getting me very, very accurately, person with 90% confidence. And it's picking up on something in front of me, which is incorrect, but that's fine. It's not being trained on this microphone. So of course, some things it might not recognize, and it'll just do its best guess as to what it might be. But of course, you could add more training data to get around these situations in the future, so it can recognize these more exotic objects that are in the room too. Or, I'm pretty sure that the confidence for this would be very low, so you can just have the threshold of recognition to be higher, and then you can get rid of these false positives if you wish. But as you can see, this works really well in a web browser. And what's key to note here is that this is all being classified in JavaScript in Chrome right now. And that means none of my webcam imagery is being sent to a server for classification. So my privacy is preserved. And that's really important in today's world, especially over in Europe, where there's GDPR rules, or maybe you're trying to make an application for medical applications or legal applications. You don't want to send the raw data to the server for classification. And here, everything is happening on the client's machine in the web browser. So very, very powerful stuff. And for TensorFlow.js, you get the privacy for free. Now, moving on to the next model, you can see I've also got face mesh here, which is just 3 megabytes in size, and it can recognize 468 facial landmarks, as you can see from the nice animation on the left-hand side. In fact, we've just updated it to even track the irises of the human eyes, so you can see more granularity around when the eye is moving, opening and closing, that kind of stuff too. And we're starting to see lots of interesting applications come out for this now from real-world businesses. On the right-hand side here, we can see Modiface, who's part of the L'Oreal group. They've managed to use this for AR makeup try-on. So now, in the current times, when people can't go into the stores, they can try on the lipsticks here and see what it looks like before even buying the product. And they're using our face mesh model to do this, combined with WebGL shaders, some nice fancy 3D graphics, to then color in her lips very precisely. So the girl on the right-hand side here is not wearing any lipstick. This is completely rendered live in the web browser, as you've seen on the left here. So really, really cool stuff. And again, let's show you face mesh in action because it's a really cool model. So let me just bring over my second demo. And you can see, once again, I'm being recognized in real time as I speak to you here today on the left-hand side doing the machine learning. But because this is JavaScript, we can just use 3.js to then render a 3D point cloud of all the points that have been recognized coming back. And you can see here, as I'm talking to you, as I blink my eyes, as I open and close my mouth, the 3D point cloud is updating in real time. And this is the power of JavaScript. What will take you maybe weeks in other languages to whip together an amazing 3D demo like this, you can do in a few hours in JavaScript, maybe even minutes if you're particularly proficient in 3.js. So really powerful stuff. Now, some of the keen-eyed amongst you may have realized that right now I'm getting a good frames per second here, and I'm executing on WebGL. And that means I'm using the graphics card to do all the mathematics that this machine learning model needs to execute. And typically for these larger models, WebGL is a great execution environment as you can leverage the graphics card's power. Now, if I switch this to WASM, which is WebAssembly, this is basically going to drop the frames per second slightly because I'm now using the CPU to execute, but it's still pretty fast, as you can see. There's nothing wrong with that. But there might be situations where you want to keep the graphics card for maybe 3D game graphics that you're trying to do and have the CPU do the machine learning, or vice versa. Maybe you want to swap it around for some reason too. So with TensorFlow.js, you've got the choice of executing on different backends, which we'll get into more later in the presentation. So that's face mesh. Let's go back to the slides and see what else we have in store. So the next one is body segmentation. This allows you to distinguish 24 body areas across multiple bodies all in real time, as you can see from the animation on the right-hand side. You can see how the different colorings of their arms and legs and heads show the different parts of the body. But even better, we've got the pose estimation coming back as well, these blue lines which estimate where the skeleton is. And that basically means that you can do some very interesting things, such as fitness workout counters to understand how many repetitions you've done, because you can track where the poses are and that kind of stuff. So let's go ahead and see some of how I've managed to use these models in some creative use cases. And as I said, with a bit of creativity, you can take these very simple out-of-the-box models and turn them into something very special. And the first one I want to share with you is an invisibility cloak. So here you can see me being removed in real time from the video feed. And on the right-hand side, you can see that I'm being removed. However, I'm still updating the pixels that I'm not in. So you can see here the bed deforming as I get on the bed to give this very ghostly Harry Potter-like effect. And, it's not perfect. You see my arm kind of show very briefly for a second there. But I made this in just one day of coding, so bear that in mind as well. This was very easy to create using the body pix model. If I understand where my body is, I also know where it is not. And therefore, I can update the video pixels where my body isn't to keep those updating over time, and just remove the ones where my body isn't, and just use the last known good pixels for those areas to get this really cool effect. And this is available on GitHub for you to try live if you want. Just search my name and you'll find this invisibility cloak for you to try out in the browser. Someone from the community also combined with WebGL shaders to make this cool laser effect. And you can shoot lasers from his eyes and mouth now in real time in the browser. Buttery smooth, works very, very fast. And again, this, I think it's called Shader Toy or something like this. It's a website you can go to and try this out online. And it works really, really well. So you can see here how you can use it creatively. Maybe if you're working with a movie client, you can bring their superheroes to life or something like this very, very easily. And why not stop there? Here's another example I use for teleportation. And again, we've all dreamed of teleporting ourselves like in the sci-fi movies. And here I can use web real-time communication, or WebRTC for short, combined with WebXR, which is mixed reality, using Mozilla's A-Frame, and 3.js, combined with TensorFlow.js to then take my segmentation of me in my bedroom, transmit the segmentation over the internet to some remote mobile device, and then that person can place me in their room as if I really was there talking to them. And I made this because in the quarantine times that we're living in, it's very hard for me to talk to my friends and family back home in England. And when you're talking on a video call like we are today, you're stuck in this rectangle and it's not very personable. Whereas if you have something like this, it can feel like the person is actually there with you. And you can even have spatial audio, so you can hear the person from the correct part of the room as you turn your head and all that kind of stuff. And in the future, I believe we will have AR glasses that people will be wearing, which are much more commonplace as they start to get more stylish. And instead of having to hold your mobile phone up like you see here, you can just summon someone to be projected in front of you as if they're teleported right in front of you. And I think that's the future of communication as humans as we go forwards. Or how about more practical applications? Here, I don't know about you, but I really struggle to know what clothing size I am. I buy clothes like once a year, and I never know what size I am for all the different brands out there. So I use TensorFlow.js on a website to automatically detect my clothing size. I enter my height, I stand once to the front, once to the side, and within 15 seconds, it can give me all the key body measurements I need so that the website can automatically select small, medium, or large for the t-shirt I want to buy or whatever it might be. And this is great because it saves me time as a consumer, and it saves the business a lot of money because they don't have to handle returns and all this kind of stuff as much. So a win-win for everybody there. And other people have also used TensorFlow.js for very creative things too, as you see here. Another example from the community, this guy can scan a magazine, in this case a fashion magazine, and bring the model to life in his living room using this cool 3D particular effect. And he's now able to walk up to them, inspect it in more detail. And I believe he even managed to get them to speak. They've actually made the character speak as well, which is amazing. So, and all of this is working on like a 2 or 3 year old Android tablet, I believe. So, even these older devices are capable of running the machine learning and then running these 3D graphics and getting these really cool effects. Now, the second way to use TensorFlow.js is via transfer learning. And essentially, if our pre-made models that you've seen on the previous slides do not recognize the things that you need to recognize, you can retrain them to work with your own data. And in this case, I'm going to give you a few examples that are super easy to do that. Of course, if you're more experienced in programming with machine learning, then you can do this all in code. But today, I'm going to show you 2 non-code ways to do this for some common areas. Now, the first one is something called Teachable Machine. This is essentially a website that one of the Google teams called Creative Lab created. And it allows you to retrain 3 common use cases: object detection, pose estimation, and sound detection. So if you want to recognize custom things in each one of those areas, you can do so. And of course, the best way to show you this in action is to actually show you. So let me drag across my screen again. So if you go to teachablemachine.withgoogle.com/train, you'll end up with a web page like this. And as I said, there's 3 things you can choose from. Today, we're going to do images. And what you're going to be presented with is this nice training flow, as you see here. The first thing we need to do is enter some meaningful names for the things we want to recognize. So the first one I'm going to call Jason, which is me. I'm going to recognize my face. And then the second one, I'm going to recognize a deck of playing cards that I've got. So I'm going to call this one cards. And in fact, let me just grab my cards before I forget where they are. Okay, good. So now we can enable the webcam. You can see we get a live preview of me talking right now. Hello, everyone. And I'm just going to start recording by holding this blue button to get some sample data of my face. I'm going to move my face around, get some different angles, and you'll see that starting to populate on the right in just a second. So let's try that right now. Cool. So I've got about 35 images, I believe, there of my face at various different angles. I'm now going to scroll down and click on the second webcam button. And now I'm going to do the same thing, but I'm going to do it with my deck of cards. So I'm going to try and get the same number of images and in different positions. Okay, perfect. I've got 33 images there. And all you need to do now is click on train. And we've tried to get the same number of images to avoid any biases, because if you have more images of one class than the other, the machine learning might think that's more likely to occur. So we don't want that to happen. And you can see now the model has already trained, and we now get a live preview on the right-hand side of what it sees and what it predicts. So you can see here, Jason is predicted with 100% confidence almost. Now, if I bring up my deck of cards, you can see that flips to cards at the bottom. So Jason, cards, Jason, cards. And you can see how fast that reacts. It's happening all in real time. And we managed to make this machine learning model in just under a minute, I believe. So in just under a minute, you're able to recognize something custom. And I can guarantee anyone watching here today can do this as well. Even no programming is required at this point. Now, of course, if I showed it a different rectangular object, maybe my mobile phone, it might recognize that as a deck of cards as well, because maybe it recognized that this rectangular shape is all it needs to think about. So of course, to be more robust, you need more training data, and you want to spend more time gathering more examples of the objects you're trying to recognize to make sure it has the best chance of classifying them correctly in the future. But for a simple prototype, you can see how fast this is. Now we can click on Export Model, and we can click on Download. And now you can download the model files that were produced by TensorFlow.js to then host on your own website. And then, of course, you can do whatever you want with them, just like you would do in JavaScript normally. So now that you can recognize an object, what could you trigger? Maybe you could make a smart webcam to automatically detect when there's a human in your house, or a dog, or a cat, or whatever it might be. You can detect that and send yourself an alert with some WebSockets or something like this. And it's really up to you. Your creativity is limitless here, and you can do lots of amazing things. I've even seen people recognize if their garage door is open or closed in the nighttime or daytime to then automatically close it using a Raspberry Pi or something like that. So you can even control hardware as well if you wish with this kind of stuff. So that's Teachable Machine, and it's great for prototyping. So let's go back to the slides. One moment. Cool. Now, if you want something more robust for production quality models, then we recommend using Cloud AutoML. So if you've got gigabytes of training data, so let's say you're trying to classify all the different flowers in the world, as you can see here, then you need to upload all this gigabytes of data to like cloud storage, and then you can use something called Cloud AutoML to take that data and learn from that. So once you've got it uploaded, you click to the next page here, and you can then specify if you want to train for higher accuracy, so more preciseness, or faster prediction time, so better speed on the predictions. And there's a trade-off between the two. So you tell the system if you want one or the other, and then you set a budget, and it'll go away and train for many hours. And after that time, it'll come back with the model that has the best results. And you can then simply download that model, just like we did in the previous example, but with this Cloud Auto ML system. Whoops, too far. And you can see here TensorFlow.js is highlighted, and you can then download the model.json files that you need to do that. And that's all there is to it. You've now got a production-ready model that you can use. And you might be wondering, well, how hard is it to even use this production-ready model in my own website? And the answer is really simple. In fact, it's so simple, it fits on a single slide. So let me just walk you through this code right now. So at the top here, we've got a script import for TensorFlow.js, and we've got a script import for Cloud Auto ML. So just 2 imports, nothing fancy here. We've now got an image tag for a new flower that we want to classify. In this case, it's a daisy.jpg, as you can see here. I've given it an ID of daisy in the DOM. And this is just a regular image from the internet, nothing fancy about this. This is something new that the machine learning model has not seen before. And then here, we want to now do the actual work. So we've got this asynchronous function called run. And on the first line here, we're calling await tf.automl.load image classification, and we're passing to it the location of the model.json file that we downloaded from the previous step. And because this might be a couple of megabytes in size, we have to use the await keyword here, which simply means this is an asynchronous operation that will take some time to complete, and we want to wait for that to finish before we continue. So once it's ready, it'll be assigned to this constant called model, and we go to the next line. So now we have document.getElementById daisy. So all this is doing is getting a reference to the image we want to classify, which in this case is the image above called daisy. And we now store this in a constant called image. And then the final line here is we call model.classify, and we pass it the image we want to classify. And again, because this might take a couple of milliseconds, which by computer standards is asynchronous, we have to use the await keyword. And once it comes back, we'll get a JSON object with all the predictions that is found for the image that you pass to it. And with that, you can then do anything you like, as we saw before, depending if it's 90% confident or 80% confident that it saw a thing. You as a programmer can then decide what to do with that knowledge and information. Maybe you're going to trigger a light to go off or open the garage door, whatever it is you want to do. So that's 2 easy ways to do transfer learning. Now, the third way to use TensorFlow.js is to write your own code. And this is for the more advanced users. And of course, to give you a whole crash course on writing TensorFlow.js in pure raw form would be a whole lecture in itself. But I'm going to focus on the superpowers and performance benefits you can get by doing that if you choose to do so. So TensorFlow.js, for those of you new to it, actually has 2 APIs. The first API is the high-level API known as the layers API, which is very similar to Keras in Python, if you're familiar with Python. In fact, if you do know that, you'll be very much at home with the layers API in JavaScript. We've also got a ops API, which is the more mathematical version of the API, which allows you to change all the linear algebra and things that are going on behind the scenes, should you want to make more high-level things in the future that don't exist yet, or maybe your own custom model architectures and this kind of stuff. So, you've got both options depending how skilled you are at machine learning. Now you can see here our pre-made models are built upon the layers API, that high-level one, and that layers API sits upon the core or ops API, as we like to call it. Now this API then can talk to different environments, such as the client side, and the client side understands, in this case, like the web browser client side, can talk to different backends. You can see here 3 different backends that we can run on. And by backends, we mean the actual hardware. So the CPU is always available. This is just vanilla JavaScript executing as normal. We've got WebGL to get graphics card acceleration, to get faster performance on the graphics card. And we've got WebAssembly acceleration, which gives you faster performance on the CPU using more lower level instructions. So these 3 environments are available to you, and depending on the model size and what you're trying to do, you might choose one backend over the other. Or you might choose to do 2 models, one running on the graphics card, one running on the CPU, to avoid any performance issues and that kind of stuff. It's always up to you how you want to run that. And the flip side is also true. We can also run on the server side with Node.js. And if you do that, we've got the same C++ bindings that Python has to the core TensorFlow APIs. And that means we have the same performance as TensorFlow Python for inference. So we've got the same AVX support for the CPU, and we've got the same CUDA acceleration for the GPU. And as we'll see later, Node.js can actually make things run faster than Python in certain use cases. And we'll go into that in more details in just a bit. So we've got the client side and we've got the server side implementations, and there are different implementations, as we'll see later. Now, for those of you already using Python, you might be wondering, well, if I want to keep using Python, is that okay to do? But can I take the resulting models and use that with the TensorFlow.js ecosystem so it's more friendly to use on the web? And the answer is yes, you can. If you're using Keras saved models or TensorFlow saved models, you can actually use those in Node.js without any performance penalties at all, without any conversions, instantly for free. And that works very, very nicely. So if you're on the server side in Node, you can take any Python generated model and execute it in Node without any conversion. You will need to rewrite the pre and post processing code, as we'll get into later on. But other than that, the model will execute just fine. Now, if you want to execute on the client side in the web browser, then you'll need to use our command line TensorFlow.js converter that's available to install via npm or Python pip, I believe. And essentially, you can then take a saved model from Python and convert it to the model.json format that you need in order to run it in the web browser. So you only need to use this converter if you want to execute in the web browser on the client side, okay? Otherwise, no conversion is required. So let's look at performance then. Here is a computer vision model called MobileNet V2. And essentially, you can see here for Python, it takes 7.98 milliseconds to execute the inference. And on Node.js, it's 8.81. So less than a millisecond of difference. So for all intents and purposes, this is basically the same because the server might have been busy doing something when we took this recording. So the difference is negligible. And if you actually take into account the pre and post processing, and what do I mean by that? So for those of you new to machine learning, as I mentioned before, hinted at, the machine learning model always expects numerical inputs in a certain form. And let's say you have an image. Maybe you need to resize that image. You need to convert it to grayscale. You then want to have those grayscale values normalized between 0 and 1 instead of 0 to 255. This is called pre-processing. You need to do this work in order to get it into the right format that the model can digest. And sometimes this can be very non-trivial stuff. So if you convert that pre and post-processing to be a node, you can actually get significant performance benefits because of the just-in-time compiler of JavaScript that optimizes things at runtime. And you can see an example here, case study of Hugging Face doing this for the Distilbert implementation. Now, all that fancy word means is that we're doing some natural language processing here, and this is to understand some human language stuff. But by converting the pre and post processing steps to Node.js, they saw a 2 times performance boost over Python equivalent, which is amazing. That's like really, really great. And it could be the difference between something running in real time or not. Now, I want to focus here also on the superpowers you can get on the client side if you do choose to convert and run in the web browser. The first thing is privacy. As we hinted at before, everything executes in the web browser if you run it there. So no data is sent to the server side. And that's really top of mind for people these days, especially if you're dealing with sensitive data for medical or legal applications. Second point is lower latency. Because no web server is involved, it means there's no round trip time from the client to the server and back again in order to get the classification. So you can run things in real time instead of having to wait 100+ milliseconds for that to happen, especially if you're mobile. The third point is lower cost. If their server is not required, then you don't need to have the server with the big expensive graphics cards and RAM and processor power running 24/7. And for larger scale implementations where you might have 10,000 users a month, that can save you tens of thousands of dollars per month in server costs. Fourth point, interactivity. JavaScript from day one back in the 90s was designed about the display and presentation of information, and it's grown ever since then. And it's one of the richest languages for 2D and 3D graphics and even data visualization. And you'll find many of the demos I've shown you today, I was able to make in days, particularly hours, versus other languages, which might take me much longer to do so. And then the fifth point, reach and scale of the web. Anyone in the world can open a web page and then use the resulting content. The same is not true if you try to use Node.js or Python on the back end with machine learning, because in that situation, you have to install those environments on a Linux server. You then have to install TensorFlow. You then have to install the CUDA drivers. You then have to clone the GitHub repository, read the README, and hopefully, if you understood it correctly, you have a chance of running the machine learning. That's a big barrier to entry for a lot of people out there. Whereas here, if someone's made an example, you can just go to a web page and it just runs. So reach and scale is very important here, and shareability. Now, the flip side of it, of course, is running on the server side, as I said, in Node.js, and there's some advantages of that too. And there are situations you want to keep running on the server side. The first reason is that you can use a TensorFlow saved model without conversion. So if there's some cutting edge research that came out, it might only be available in the saved model format right now. And you can use that on the server side very easily. The second point is you can run larger models than you can do on the client side. If you've got gigabyte-sized models, some of those things do exist for very large models, then you don't want to push that down to a tiny mobile phone because that's just not going to be very efficient. So some models you want to run on the server side. And then the third point is it allows you to code in just one language. If you're already using JavaScript, and currently 67% of developers out there use JavaScript, according to the Stack Overflow survey of 2020, then you can stay using one language, which is very, very powerful. It's great for code maintainability and reusability. And for those reasons alone, it's a nice thing to consider. And then the fourth point, as we saw, is the performance benefits. We've got the same C bindings to TensorFlow Core as TensorFlow Python has, which means we have the same inference times, but we have a better end-to-end classification time, as you saw, just because of the just-in-time compiler of JavaScript. So I'm going to end this presentation with resources to get started. If there's one slide you want to bookmark, let it be this one right here. Essentially, this has all the resources you need to get started with TensorFlow.js. Our website has our API and tutorials on there at the very top. We've got even more models for you to explore. I've gone through just 3 in this presentation. We've got tens more available on our models website there. We are completely open source. So if you want to contribute to the project, you can check out our GitHub code. And I've also put together some boilerplate code on CodePen and Glitch that allow you to get started in minutes with the webcam and such, so you can pass this data to some of the existing models that we have very, very easily. And you can just fork those and play with them in the browser. You don't even need a text editor. You can just fork them live in your web browser and start playing with them over there. We've also got a couple of books coming out. This one's been around for a while, Deep Learning with JavaScript. That was written by folk on my team and people in the TensorFlow team here at Google. It's aimed to be a good introduction. However, at times it can get a little technical, but it's still a good book overall, highly recommended. However, there's also another book coming out very shortly from O'Reilly, from one of our Google developer experts, Gant Laborde. And I've been technically reviewing that book for him, and it's really, really good. If you're a beginner to machine learning and JavaScript, or just new to this area, then that's a really good book for people who might be newer to this stuff. So do check out those 2 books as well. So with that, my only thing left to say here is come join the community. There's tons and tons of demos coming out from people just like you all around the world every single week. I can't put them all into one presentation, but you can see here, if you check out the Made with TFJS hashtag on Twitter and LinkedIn, there's tons of inspiration for you to see what other people are making out there every single week. And if you do make something cool, make sure you use the hashtag Made with TFJS, as I have a quarterly show and tell on our YouTube channel that goes out to, I think, 250,000 people. And if you've done something really cool that I've not seen before, then I will typically invite you to come talk about it with me and nerd out with me on that show. And I also have blog posts and things going up all the time. At the very least, I can share your work and get more eyes on it for you. So with that, a little bit of inspiration again. This is a dancer from Japan in Tokyo, and he's managed to use TensorFlow.js to make this really cool hip-hop video, as you can see here on the slide. And my reason for ending with this is that machine learning really now is for everyone. It's not just for the academics and engineers, but it's also for the creatives, musicians, and artists as well. And TensorFlow.js is a key part of that story to enable anyone to be able to use machine learning. And I hope that everyone here today takes their first steps with it as well. Even if it's just something simple, just go and try it out after the show and tag me with Made with TFJS to see what you've made. I'd love to see what you've been creating. And with that, get creative and innovative, and feel free to stay in touch with me. I'm at Jason_Mays on Twitter, and I'm Creative Tech on LinkedIn, as you can see there. So feel free to add me on those 2 areas. And I post about all this stuff all the time, so it's a good way to keep in touch. And for now, I'll take questions. So feel free to type in the text chat, or maybe even unmute if you've got a question that you want to ask right now. Thank you very much.
Thank you very, very much, Jason. So we can start with the questions that we have here. Before moving on to the questions, I would like to add something on the Node.js and running TensorFlow on the JavaScript with JavaScript. Is that You can also use TensorFlow.js with desktop applications. You can use the Electron.js framework, provide executables for all platforms, Linux, Mac, Windows, and you have your application bundled in a single executable file. And then you can run like some really large data sets and models there. If your model weighs like to the hundreds or megabytes, you can pack it, make it a desktop application, and you can just publish it this way, and it can run offline. So that's also another like really cool aspect, I guess.
Yeah, totally.
So
we've seen a few companies start to do that as well. Actually, we've seen people do these like analytics for small, medium-sized businesses to kind of do prediction engines on data that they wanted to keep local and not have it sent to a server somewhere. Like small businesses wanted to keep their data locally on their servers. And we've seen people make Electron apps for exactly that reason, in fact. So yeah.
Exactly. And so the question, I think it's kind of, you answered it. What's the difference between strong AI and weak or narrow AI? Would you like to go more into it?
So just to kind of recap that one is, so strong AI is the stuff that you probably see in the Hollywood movies that we do not have right now. That is, I guess, very far away. That's trying to replicate consciousness itself, which we don't even know what consciousness is these days, right? So no, we're nowhere near that, and that's just an illusion of the Hollywood movies. Weak AI or narrow AI, as I called it in my presentation, is where we are living today, and that's simply being able to replicate certain abilities that humans have, like object recognition, in very narrow fields, but it can do it very well. So it can do those things as well as a human expert, sometimes better than the human expert. So very niche fields are where we are able to do things right now, rather than this generalized thing that can just adapt to any situation. That's a much harder problem to solve. And if you look at my other lectures online about what a neural network actually is, and there's a Machine Learning 101 course on YouTube you can take. I got like a slide deck you can go through, and I explain like how this actually works behind the scenes. It's just a bunch of mathematics. It's not conscious. It's just mathematics. So if you think about it like that, you'll realize that yeah, okay, it is just maths working out, and it doesn't understand when I present to it my deck of playing cards that it's a deck of playing cards. It just knows that it's this rectangular kind of shape, and it doesn't even know what a rectangle is. It's just got these like kind of filters, if you will, that it's using to kind of extract edge detections and things like this, and then it uses that to then say, this is probably the thing I saw before, but it doesn't really know what it is truly, like you and I understand what it is. So very different to that kind of stuff. So simple, but very powerful, as we've seen. So yeah.
I don't know about your time. So do you think we have...
I can do a few more minutes, whatever you want to do. Yeah.
One more question. Okay. So in your opinion, says the question, how will AI impact application development?
Yeah, I think as web app developers or just even regular app developers, like people are going to be more mindful of what's available and possible with machine learning to enhance their applications, to give them an edge over their competitors and that kind of stuff. And as I mentioned at the beginning in the pre-chat, like every industry has a potential to be influenced or affected by machine learning. So next time a client comes to you and says, hey, I want to have this kind of support system that allows me to put tickets into the right support category, instead of having a human read that ticket and put it to the right email thread, why not use AI to do that instead? And it's possible. You can use natural language processing to automatically say, okay, this is a ticket that's probably needs to go to engineering. This is something that goes to sales. This is something that goes to marketing. And that level of categorizing things is definitely possible these days. And that will save you a lot of time. Your client's going to be super happy because they don't need to hire an extra person to do that one job. And that person can be used to do something more useful within their company instead, rather than just reading emails all day long. So yeah, think about how you can optimize flows there.
And that's exactly what we're going to do next. We're going to use categorize words and sentences. Now, another question says, is there a JS machine framework for TinyML, embedded systems, Arduino boards?
Off the top of my head, I mean, I only day-to-day get involved in TensorFlow.js, so I'm unsure about that. Maybe somewhere on GitHub that there are other like smaller libraries out there that might be doing specific things for specific platforms, but In terms of getting all the support on the different types of backends, like I spoke about today, I believe TensorFlow.js is one of the only ones that supports all these different backends like WebAssembly, WebGL, and this stuff to get you the faster acceleration. So maybe there's others that exist on these other platforms, but it might not be as fast. So yeah, maybe someone can try it and test it out and see if you can get it to work on those platforms. I'm not sure, but you might need to use other forms of TensorFlow, like TF Lite or something, to work on microcontrollers, for example. So even though we support Raspberry Pi, traditional microcontrollers, you probably wouldn't use TensorFlow Lite for that kind of stuff. So yeah.
Okay. Do you have time for more questions?
I can do one more question, I think. Yeah.
Okay.
Yeah.
So I think this is interesting. To use a TensorFlow.js model on the client side, does the model need to be hosted on a server, or does it get downloaded in the client side?
Yeah, that's a great question. So initially, it does need to be hosted on a content delivery network or your web server somewhere. But once the page is loaded, you can store it in like local storage or some local database on the client side. Those technologies exist these days in the web browser. And then you can have it run completely offline after that point if you wanted to do so. So you should check out progressive web applications that are designed to work offline. And if you make a progressive web app that uses machine learning, then that's a perfect use case of you load it once and then it will be able to work offline thereafter using web workers and this kind of stuff. So that's definitely possible and is one way to do that. Yeah.
Okay. I think we covered a lot of the questions. I will be able to answer some.
I just see one interesting one, actually. I just saw one cool one come up there. So will TensorFlow.js be used in game engines in the near future or still in primitive state? So that's actually a question for the game engine developers out there. If you're involved in game engines in JavaScript, then please go and integrate it. We've seen people actually experiment with reinforcement learning in JavaScript. There's a whole group dedicated to that somewhere on the internet. They're starting to form now. So if you're interested in those kinds of things, check it out. There are some demos for reinforcement learning in TensorFlow.js where they can control cars in these like 2D games, and they learn to drive by themselves, like self-driving cars in 2D, which is kind of cool. And they learn by themselves to do that using reinforcement learning, which could be really cool for a game or something like that. So definitely check out those demos. And yeah, these are early days. Our team has only been around for like 3 years versus TensorFlow Core, which is like 6 years. So JavaScript is still very new for machine learning, but it's going to move very fast. And as I said, the 67% of developers are using JavaScript. There's potential for this to be even bigger than Core in the ultimate future. So it's up to you guys and girls to actually make some of these things and contribute to the community. And hopefully we'll have amazing things in the future that allow us to do all this stuff. So please do integrate it with other things and let us know if you do, so we can share the love and help people try it out.
Yes. So thank you very much. We're really, really grateful for you being here, and we're really grateful because you are here during working hours. We had like a big problem trying to get the perfect days in time for this big gap in time zones. And thank you for making this possible during working hours. You can find the links on the document, everyone. We will have a coding session afterwards. So thank you, Jason.
Problems? Yeah, I've got to run off to another meeting, but basically feel free to add me on LinkedIn and Twitter if I didn't manage to ask you your question today, and just let me know that you met me here. Otherwise I'll get all the invites and not know who is actually real or not. So just add a message to your invite and I'll talk to you over on LinkedIn or Twitter. So thank you very much and see you soon. Cheers. Bye-bye.